Okay, so I'm going to talk about the joint work that we made with Roberto Bruni, Roberto Giacobazzi, who is here, Roberta Gori, she's in some place, I don't see him, and myself. So it's the work of last year that we... that we published at Leak Symposium. I have to say that the real title of this talk is not... is Patrick Couzeau, the greatest true scientist I ever met in my life. And so you see the picture showing that he's a true scientist because he has doubts. And yeah, I have to say that thanks, Patrick, for inventing abstract interpretation because it changed my scientific life for sure. And Patrick, we have some memories together. Actually, these memories... Yeah, that memory... it doesn't work, the pointer, but this one is when we try to solve the Monio problem in a more general setting. And here, in some cases, Patrick is very happy, in some cases not so, he's a little bit upset. Does it work? Yeah, but managing two is not easy. Okay, good. So let's go back to the talk. So we are talking about a program logic. So we need the program semantics. The program semantics is more or less standard. So we have a denotational semantics for a Turing complete language. So we have a precondition, a set of input stores. We have an output store. The program could diverge, and so we have a model of divergence from this standard denotational semantics. We get a collecting semantics, so a transformer from state properties to state property, from precondition to postcondition, and the postcondition is the strongest postcondition. Okay? There are some animation here made by the colleagues of this paper. So what we want to do is program verification. So we want to check if given an input property, our program satisfies some spec. And in case this is not true, we want to find the bug showing that the spec does not hold. So here, in this case, the spec is satisfied because all the traces of the program are included in the spec. But if we change the precondition, then we could have that the property, the spec is not satisfied, so we want to find the bug. One could use some symbolic approach as a program logic for proving that the program is correct, and the most popular, I would say, symbolic approach is OR logic. OR logic is an over-approximation logic. That means that when you prove a triple PCQ, Q is an over-approximation of the strongest postcondition of the program for the input P. Okay? And so you could do a proof in OR logic for proving that your program is correct with respect to spec once your postcondition implies that spec. So this is the case when your Q, what you prove, actually is an over-approximation that does not intersect the bad state, so it's included in your spec. But what is the problem in this over-approximation based program logics is that when the program is not correct, you cannot conclude that the program is buggy. And so over-approximation or logic are not good for doing bug detection. Okay? So one could reverse the approach, and this has been done by Peter O'Hearn 2 years ago in Popular 2020, and he proposed the so-called incorrectness logic. So OR logic is a correctness logic for proving that the program is correct, and incorrectness logic wants to prove that the program has a bug. And so it's called incorrectness logic. And the approach is the dual of the approach of our logic, so it's based on under-approximation. So here, the post-condition is not an over-approximation of the strongest post-condition, but rather is an under-approximation, so is contained in the strongest post-condition. Why is this useful? Because if you have an under-approximation, that Q there, then when you prove that your Q has a bug, then the program is buggy. Okay, so in that case, when you have your post-condition Q, which is in yellow in that diagram, and the yellow contains a bug, then your program is really buggy. On the other hand, when you follow this approach, so when you use an incorrectness logic approach, what you cannot do is to prove that the program is correct. So incorrectness logic is there for proving that programs are buggy. So incorrectness logic was a success because it was already implemented, I think, in Facebook. I can check with Francesco Logozzo. Is that true? Yeah. So it's already been implemented. Peter O'Hearn stated that the challenge of designing incorrectness logic actually came from the software engineers in Facebook. So there was a practical goal in designing this logic. And it was quite successful. There is already an incorrectness logic for an incorrectness separation logic. So there is some hype around incorrectness logic. But incorrectness logic cannot be used for proving that the program is correct. So our goal was to combine the correctness logic and the incorrectness logic in order to have a logic which is able to prove both that the program is correct and that the program is buggy. So our approach was based on under-approximation because our post-condition Q is an under-approximation of the strongest post-condition. So it's the yellow one included in the blue strongest post-condition. But in our logic, we add an abstract domain A, an abstraction of the stores. And why is useful to add an abstract domain there? Because we want to have this property. So Q is an under-approximation of the strongest post-condition, but the strongest post-condition is over-approximated by the abstraction of Q. And so the strongest post-condition is in between Q and the abstraction of Q. This is useful for proving both correctness and incorrectness when that equivalence holds. So Q is contained in the spec if and only if the abstraction of Q is contained in the spec. And so in that case, the diagram shows that the post-condition Q is inside the blue area, which is the strongest post-condition, and the blue area is inside the orange area, which is the abstraction of Q. So in that case, in this simple program, which is the absolute value of a variable, so if you take as an input property -7 and 0, this is the precondition. The postcondition is 0 and 7. Okay, let's use the interval abstraction for doing an analysis of this. What can you infer in this case? You infer that you do the analysis, so you infer doing all the transfer function, you select, you split on the left, you go on the right, you do all the stuff that you want, and at the end you wait a little bit the output of your abstract interpreter, and you get 0,7. Okay? This 0,7 is quite lucky because 0,7 is the complete result of your analysis. So complete here means that the strongest postcondition is 0,7, and if you abstract the strongest postcondition, you exactly get the interval 0,7, which is the output of your abstract interpreter. Okay? And so in this case, we have completeness. in this specific example of analysis of this little program. Its completeness, good question. Its completeness, yes, I was too fast in commenting that completeness. Its completeness, we have to wait the output. Its completeness in the sense that the output of the analysis is the same of the abstraction of the strongest post condition. Okay, I change the input now. I consider -7 and 7 as input of our program. I do the analysis, and the output in this case, so you see, I go on the left with -7, I go on the right with 7. The absolute value of -7 is 7, and so there the result is 7, 7, the abstraction of the strongest post condition. But the intervals lose precision in this case, and so we still get 0, 7, so in this case we are incomplete. But this is old stuff, more or less. So what was our idea? Our idea was to, before the idea is an observation. So if you want to have completeness for all the input properties and for all the program, there is no chance of getting this, let me call it, global completeness. Why? Because there is some prior work of 7 years ago stating that, if you want to be complete for a Turing-complete language, there is no hope unless of using a trivial abstraction. And trivial means you have in any case, I don't know, or you are on the concrete side of getting this global completeness. This was a result that we made with Francesco. Okay, so the idea is, okay, we have to throw out the global completeness objective, and we have to focus on what we call local completeness. So we want actually completeness for some specific input property and for some input property for a given specific program. And so we are interested in the same equation of completeness, but for a given program and for a given property. This is called local completeness. And what happens is that if you consider this weaker notion of completeness, this local completeness is a convex property, meaning that if you have a local completeness for some property P prime, then you have local completeness for any P which is in between P prime and the abstraction of P prime. And this property is the key for getting the key rule of our program logic, which is the consequence rule that combines the logic of Tony Hoare and Peter O'Hearn. Because look here, what we do is we do a strengthening of the post condition. So if you prove the Q prime, then you can strengthen Q prime to Q, which is contained in Q prime. So it's another approximation, it's stronger. But we put a further constraint. The constraint is that when you abstract Q to A of Q, Q prime is in between. This is for the post condition, and dually we do that for the precondition. So the precondition is weakened, but with the additional hypothesis that the weakening is in between the abstract of what you have already proved. Okay, so this is our consequence rule that in some sense generalizes the consequence rule of Peter O'Hearn and inject a reasoning which is a reasoning both for proving correctness and for proving incorrectness. What are the basic axioms of our program logic? We require local completeness for all the basic expression of our program. So for all the Boolean guards and for all the assignment that you have in your program, We just ask local completeness, not global completeness, for our input property and for our domain. And so, yeah, we call that rule the transfer rule, transferring for the basic expression. So that is for assignments and for Boolean guards, which are the basic expression of imperative programs. This is the proof system. I just comment on this rule for, actually we use it as language, the regular languages, which is the same language that you find in a Kleene algebra with test. And let me just comment the rule for the Kleene iteration, the R star, the Kleene star. Why that? Because that rule has among the premises the use of the abstraction A. And so when you find that the post-condition is stronger than the abstraction of the precondition, then you can stop your computation, and then you can conclude the disjunction of P or Q. And that means that actually what you have found is an abstract invariant. That abstract invariant is the abstraction of P. This system is sound, meaning that when you prove a triple inside this system, what you have is, let me just comment here, you have another approximation of the strongest post condition, and what you have is that the strongest post condition is below the abstraction, the analysis of your problem. And so this is exactly what we were aiming for. We also, what we have, yeah, more or less I'm running out of time, so let me just tell you that we have also a result of logical completeness. So if we require that our basic expressions are complete in a global sense, then the proof system is complete, and we have some intrinsic completeness results that I skip. More in the paper, yes. Let me just mention some future but also current work. So we went on, and in the end, what we did is that we design an abstraction refinement strategy to combine with this program logic. And in the end, what we get is a new, let's say, paradigm for doing program verification based on local completeness and refinements of abstraction in order to get local completeness. And this paradigm is called abstract interpretation repair, and it will be presented in the next PLDI. The future work that we want also to do is generalize incorrectness separation logic using our machine. That's it.
Thank you for your talk. Any question? No? Yes. And Patrick.
So you have some pretty strong requirements on how what the abstract domain should do, right? And what kind of under approximation you can use. What can you give as a kind of practical examples of domains that and under approximations that satisfy these properties?
The domain is an over-approximating domain. So the domain is standard, let's say, so you can use interval, octagons, or whatever you want, and gives you the upper bounds of your post condition. But the post condition is another approximation of the strongest post condition. So no, there is no constraint on the abstract domain, except, of course, that you have to start your proof from basic expressions which are locally complete. Yeah, that's of course it.
Thank you. So I had a stupid question, as always. I was thinking maybe the incompleteness logic is obtained by negation.
Incorrectness, you mean?
The incorrectness, yes. So you take the whole logic, you try to put proof not P, and then you push the negation back through everywhere, like not pre of, pre-tilde is not pre of not, so you can push your negation.
So you negate the condition in your over-approximation proof,
Yes,
and then you get some...
And then you get rid of the negation by applying the Morgan, the fact that post become pre and so on. And I was wondering if you get incorrectness logic, and if not, why?
I think no. I think no, and so I never thought in detail to this question. The question makes sense. I never thought in detail. I think the answer is no, so you don't get incorrectness logic. Why? I don't know. I don't know.
Because word is always defined as not correct.
We did actually, we didn't consider pushing negation What we tried is to use, rather than over-approximating domain, using under-approximating domain, but we failed. We failed. We failed.
So you don't know the answer.
No, I don't know the answer.
You don't know who will know it.
Thank you.